guitar pedals, and effects pedals more broadly have become essential tools for shaping sound. They allow musicians to modify their tone in real time, adding layers of depth, ambiance, distortion, rhythm, or harmony. Whether used sparingly for subtle enhancements or in complex chains to create entirely new soundscapes, pedals are central to modern performance. Most commercial pedals are built with specific, often limited functionality. So our goal was to create something more modular and expressive, a tool that not only offers control over delay timing and feedback, but also integrates pitch manipulation at the beat level with the sequence. This enables the performer to treat the pedal as more than just an effects unit, and in fact, it becomes a part of the instrument itself. Our pedal offers two primary features, divided into its own individual sub-features. The pedal takes an audio input from a guitar and plays it back on a user-defined delay sequence. Each beat in that sequence can be individually enabled and disabled, and the user can customize the delay interval as well as how much the volume attenuates with each repeat. Additionally, each beat can be pitch shifted independently. The user is given an option to pick between two modes, 3-beat mode and 4-beat mode, in which the user has an option to either select from 1, 2, or 3 out of 3 beats, or 1, 2, 3, or 4 out of 4 beats. What sets our pedal apart from most standard delay pedals is the per-beat pitch control, and the ability to define that sequence manually in real time. The result is an effect that can be musical, or rhythmic, or chaotic, depending on how it is configured. We have two rotary encoders. The one on the left controls amplitude attenuation, and the one on the right controls tempo. We also have 4 LED buttons. We can turn LED buttons on and off, and when you do so, if it's on, that means that the beat is selected, and if it's off, the beat is not selected. We also have a 2-mode switch that controls whether the user wants to select 3 beats or 4 beats as part of their delay feature. All of this is in standard mode, which is the first mode indicated by the 3-mode switch. The second mode indicated by the 3-mode switch is the pitch shifting mode. For this, we also have the 4 LED buttons, which you can select one at a time, and when you deselect a button, the previously selected button value is still saved. Now I'm going to be talking about the software portion of our project. We implemented pitch shifting via the phase vocoder algorithm. The typical setup is to time stretch or compress audio while keeping the pitch the same, then resample but for a real-time application. We had to be careful to keep the time the same. The phase vocoder takes the discrete Fourier transform, which we programmed as well, at windows throughout the signal. It stores the magnitudes and phase differences, that is the current phases minus the previous phases throughout the signal. The rate at which windows occur is multiplied by the pitch shift factor, and output windows are created by interpolating from the input windows. The inverse discrete Fourier transform returns the windows to the time domain, and they are inserted, resampled, and interpolated into a circular buffer, waiting to be outputted. There is some inevitable latency, as each sample must wait for the completion of each previous input window. Nevertheless, this process preserves the phase relations between each successive window, and keeps the signal clear and audible. Also, the echo operations are fairly simple, storing the input sample in a circular buffer to be outputted at a later time. Now we'll show some portions of our software working. Delay feature of our pedal. Here we have one of our group mates playing the guitar and using the pedal by selecting the beats they want, the tempo, as well as the amplitude attenuation as is listed. move on. Unfortunately, the pitch shifting feature of our pedal is not fully operational. However, while we were not able to integrate the full implementation, individual implementations of this feature were operational. The hardware interface shown earlier showed that we were able to get the hardware Overall, we had a few setbacks throughout the whole process. We ran into issues with components early on, especially due to the current issues with trade in the world. As a result, many parts got delayed, and this kept setting back our progress for initial demos. To deal with this in testing, we made a breadboard prototype based off the schematic, which was functional as intended. The delays led us to receive the PCB later than we had hoped for, and after a few initial tests and finding that there was some issue, we decided to have a devboard version of the breadboard prototype to have working. We have not been able to find the issue with the PCB, but as other versions based on the schematic work, we believe it is just some small issue in fabrication. We also learned that the DAISY microcontroller may not be the best microcontroller for our use. This was evident in the full integration and the tough situation that we had when trying to integrate everything together. Overall, while we worked really well together, we learned a lot throughout the process. There are many things we could have improved. While there are several obstacles and roadblocks that we had to overcome, our group worked very well together to get a functioning delay pedal and a semi-functioning pitch shifting pedal. We hope that users can have fun with our pedal and improve on it as needed.